Good day, everyone. Robert Wilson here, looking at Q Learning Agents, video for our discussion post. This is for University of Central Florida, the Model and Simulation Degree Program, studying under Professor Dr. Sean Mondesiri. For this presentation, we're going to look at the frozen lake environment, the Q Learning Agents plus their hyperparameters, regression classification, the reward progression as they were training, and episode selection. For this Q Learning environment, we use the Frozen Lake version 1 environment by Pharma, which is a classic grid-based reinforcement learning scenario. The environment is a 4x4 grid where the agent starts at one corner and their aim is to reach the goal at the other corner. Along the way, they must navigate across frozen surfaces while avoiding holes that will cause the episode to end or be truncated. The goal represents by a specific tile, gives the reward of 1 upon being reached, which you can see in the bottom right corner. Now, in this version of Frozen Lake, we disabled the slippery condition, which means that if the agent attempts to move in a direction, occasionally they will slip and move perpendicular to their desired direction. We have that disabled in order to make it a deterministic environment. This means the agent's actions are executed as intended without any randomness that the slippery condition introduces. This setup simplifies the learning process for the Q Learning agents. In this project, I used 3 different Q Learning agents based upon a single Q Learning agent class, feeding in different learning rates, discount factors, and epsilon decay rates to give variety to the agents themselves. The first was the low exploration agent. This agent is programmed to explore less aggressively and exploit its learned behavior sooner. It uses a slower epsilon decay, meaning that it spends more time exploring initially before focusing on exploitation later on. Next, the high exploration agent. As the name suggests, this agent explores more than the low exploration agent. It continues exploring for longer due to a slightly lower epsilon decay rate. This gives it more chances to learn the environment to find multiple routes to the goal before it converges on a strategy. And then finally, we have the greedy epsilon agent. This agent reduces exploration rate, shifts to exploiting the best actions as learned early in training. It's designed to converge fast, but the risk of potentially missing out on better strategies if it cuts exploration too soon. The greedy epsilon agent is also the one that if it did not find a solution relatively early with its cut epsilon rate later on, it would never find a solution. So the hope was that it would find one quickly and then begin using it right away. In learning rates, they were kept at 0.1 for the low and the high exploration for the hyperparameters, and it was used as 0.5 for the greedy epsilon, which controls how much they learn from new experiences. And then for variation, we used a discount factor of 0.99, which means that they heavily prioritize future rewards, and then that discount factor was slightly adjusted for each of the agents. And then finally, for the agents, we varied the epsilon decay rate, determine how quickly it begins to prioritize utilizing the high values of the Q table over utilizing exploration. All right, looking at some of the results, the classification results for all 3 agents achieved perfect classification scores with 100% accuracy, precision, recall, and F1 scores. This indicates that the agents perfectly classified the optimal actions for their state based on their learning Q values. Essentially, they fully learned the best actions for each possible state in the environment. And this was over a utilization of 500 runs. Looking at the regression results, here we can see some subtle differences in how accurately the agents learn the optimal Q values. The mean absolute error shows that the high exploration agent had slightly lower error when compared to the greedy epsilon agent and the low exploration agent. This is just that the high exploration agent slightly outperformed the others in learning more accurate Q values. Similarly, the root mean square error was lowest for the greedy epsilon agent, meaning it had the smallest prediction errors overall. While the classification performance was perfect, these small differences in regression metrics identified that the greedy epsilon agent was more efficient in learning the optimal strategy. Looking a little deeper into their reward progression, the low exploration agent had a slower start, but it showed steady improvement over time. It took longer to converge to optimal behavior because of its conservative exploration strategy. As it explored for a longer time, it took more episodes to start exploiting its learned behavior. The high exploration agent performed more consistently throughout, though we do see some fluctuations before it finally stabilized, and that would be the orange line there, before it stabilizes around the high reward. This is expected due to its more balanced approach between high exploration and exploitation. And then finally, we look at the greedy epsilon, or the greedy epsilon agent. This one stands out. It quickly reached high and stable reward learning very early in training. Because it focuses on exploitation early, it's able to settle on a good policy faster than the other agents. However, it is worth noting that the aggressive strategy can be risky, because if it does not find a solution early on, it may never find a valid solution. If there were more randomness, or if the environment were more complex, it might not have been able to find an optimal policy so quickly or even at all. Selecting the right number of training episodes is kind of important. I found that 500 episodes was a good balance between success and redundancy. Usually by 500 episodes, all three agents were successfully able to find the goal and accumulate their rewards. When we tested 300 episodes or less, the agent typically failed to find optimal solution at all, never finding a reward, never making a valid complete queue table. This was especially true for the low and the high exploration agents, which needed more time to explore before they could settle on effective strategy. And for the greedy algorithm, if it did not find one early on, then it did not have enough episodes overall to find anything. On the other hand, training beyond 500 episodes showed diminishing returns. All agents had already converged by this point, so more episodes didn't add much benefit in terms of learning or reward accumulation. Additionally, even with 500 episodes, there were occasions when the greedy agent never found a solution. I tried using the ANOVA and the Tukey HSD results. I'd never used this results solution before, so it was a little unique, and it didn't give the results that I expected because I encountered some issues. The reward distributions for all the agents were almost identical, and because they were almost identical or so consistent, the ANOVA test results returned not a number, meaning that the F statistics could not be calculated. We also attempted to run the Tukey HSD to compare the means between the agents, but again, due to the identical nature of the rewards, the test result returned no meaningful results. And that's because they either had a 1 or they didn't, and most of the algorithms would figure out their results relatively early on, and when the tests were actually run later on, they utilized the Q table to be successful every single time. Therefore, there was no difference between one and the other, which returned unexpected results on the ANOVA and the Tukey. All right, everybody's favorite slide, conclusion. So all three agents succeeded in learning the optimal policy in the frozen lake environment, especially after 500 episodes. The epsilon decay rate played a key factor in how quickly each agent converged to an optimal solution, with the greedy epsilon agent converging the fastest, if it found solutions early on. Classification metrics were perfect for all agents, but regression metrics showed that the greedy epsilon agent was slightly more efficient in learning the correct Q values. With 500 episodes, we found this was the ideal training length, while less than 300 resulted in never finding a valid reward or a valid solution to the problem. Overall, the study highlights the importance of balancing exploration and exploitation and tuning the hyperparameters appropriately, and training agents to be for sufficient episodes to ensure learning success. And squeezing in just under 10 minutes, which is our max time for this one. Apparently 13 minutes last time was too long. We utilized the OpenAI Pharma Gymnasium frozen lake environment, which can be found at this hyperlink here. All right, thanks.